Hello and welcome to this video on Deutsch-Jozsa Algorithm. So we are going to try and solve problem using this algorithm. So what is the problem? And even we can say that this is one of the first algorithm that can prove the quantum advantage over classical computer. So it is very important for us even though we are not going to use it in real life problems. So problem over here is that we have a function, so we don't know what that function does, but we know that it actually takes either 0 or 1 as an input. So we can give a 0 or 1 to the same function, and for the output we have four possibilities. We have either 0, 0, 0, 1, 1, 0 or 1, 1. So if the output is same like 0, 0, then we call this function a constant function. Okay, like in the case of 0, 0 or 1, 1, we call this a constant function. But if the output is 0, 1 or 1, 0, then we call this as a balanced function. So what does it mean? It means that the output actually does not depend upon the input in case of constant function. So whether we give 0 or 1, we are going to get 0, 0 or 1, 1. So we call this a constant function. But if the output depends on the input, then it's a balanced function. Like consider a coin toss. So if you get a head or tail, then it means that you are dealing with a constant function. But if you get head tail or tail head, then it is a balanced function. Okay. So we want to determine whether this is a constant or balanced function with the use of this quantum algorithm. Okay, so that is our problem. Quantum computer can do this with only a one shot. We can determine whether this is a balanced function or a constant function with one shot only. So it actually proves that quantum computer can outperform the classical one. So this is the problem. We are going to determine whether function constant or balanced function. And we are going to do this only with the one shot. So we can try this and do this with the gates that we have been using and learning so far. So what will our circuit looks like? We are going to have two qubits. Okay, so for the input register and for one for the output register. So I'll call them as cat 0, cat 1, or else cat x or cat y. So we have something called black box over here. So just forget about the black box. We just have a function over here. We apply that function to cat x, cat y, and we get some output of it. So this cat x will be our measured qubit, and this cat y is something a helper qubit. So we are going to apply the function that we don't know. We just have to find out whether this is a balanced or a constant function. And in that case, if it will just give a constant, it will just give in the output of cat x. But when we apply this to the cat y, we are going to have something weird over here. That is cat y plus fx. So this sign is not a tensor product, it is a plus sign. So this plus sign means exclusive or. So why do we have exclusive or the cat y with the function itself? So remember, this has to be a reversible function. We are dealing with a reversible operation over here, something like Hadamard, and then applying it again in order to reverse it. So it means if we apply UF one more time to the circuit, we are going to get cat xy or cat x, cat y state to begin with. Okay, so we are going to have some state, and if we apply this UF on one more time, then we should have cat x, cat y state again. Lots of mathematical steps involved, which I will discuss in details in my further videos. However, when it comes to write code or just composing this in the circuit composer, we can just represent this function with anything we want. We can represent this with C naught or CZ, anything, control Z, anything. We can actually think about mathematics, then we can actually prove it with any function. So if you remember the quantum teleportation, this is exactly what we did there, right? So when we come to the actual circuit composer, we represented the state cat 1, we applied NOT gate, we can represent this. We have a function with anything that comes to our mind, like C naught, anything, and we can see whether this C naught was like a balanced function or constant function. All that matter is that it actually take one shot to determine that outcome. And why did we call this a black box? So it means that there is some function and we don't know what it does, but give it some input and it will give us some output as a return. So okay, this is a black box. So let me just open in Circuit Composer and display you. So this is the Circuit Composer. So we are actually going to build this in Circuit Composer first. Let me delete this one qubit here as we need only 2 qubits. So remember how the circuit goes. First we will start applying Hadamard gate on the first qubit, and then applying the NOT gate on the second qubit, and then again applying the Hadamard gate on the second qubit. So with this first qubit will be in the get positive state, and the second will be, after applying NOT, it will be in get negative state. I'll be using the identity gate over here because I want to make it more clear by applying the barrier over here. But if I won't use any identity gate over here, then barrier will look more messy, like this. So identity gate won't make any changes to this gate, or to its state, sorry. So yeah, so next step we would be applying C not gate. So this C not gate will be our UF function. So we'll only represent this in order to say this is a balanced function. Of course we can try this with other gates as well. So we need to measure this qubit 1 state over here, and then we are going to even do anything. We are not going to do anything with qubit second. So I am going to apply the Hadamard gate on the first qubit only, and then going to measure it. Okay, so you can see the result: 100% probability of being its in state of being the qubit in the state 1. We don't need to see anything about the second qubit, which is showing 0. I don't know why it is showing, as we are only measuring the first qubit only. So now let's try it on the okay, let's run it on Cosm simulator for more clarity. 1024, no matter, it's fine. We can run with this also. Running. Just a few seconds, then it will show the result. Okay, so here is the result: job completed. And yeah, this is actually what I want: the 100% probability of having the qubit 1 in the state 1. So now let's try it on, code it on Qiskit. So this is what I've already renamed it, Deutsch-Jozsa Algorithm. So yeah, let me import some libraries over here. Check the probability result. Okay, visualization, import, and matplotlib for more clear visualization of the diagram. After that, okay, so as we are going to focus on first qubit state, and we measure that particular state only. So we can create 2 qubits and 1 classical bits. So let's get created. Now applying Hadamard gate on the first qubit. And NOT gate on the second qubit. Then again had a mark on first qubit. Draw the barrier for more clarity. Let me draw this to check how it looks after this changes. Matplotlib, MPL. Oh, spelling. I might run it twice. Let me restart it and run all the cells. Yeah, this is the kind of circuit which I want. They had a mad gate on the first qubit, showing it in the positive cat plus state, and after applying the not gate on the second qubit, and then had a mad, it showing that it is in the cat in negative state. So after this, applying C not gate, so we are going to do this C naught over here. So we are then again we are using the, we have to use the barrier for the clarity. And then I'm going to add Hadamard gate to the first qubit, because we are only going to to focus on the first qubit state and going to measure that only. So first let me apply the Hadamard gate on the first qubit and then measure it. I'm going to measure the first qubit only. That's why I'm entering it 0 0. Classical quantum bit and the classical bit, mapping it with the quantum and the classical bit. So okay, let's run it. Okay. So yeah, this is the kind of the circuit. So now going to use the simulator for the probability. So yeah, we only use one bit, and we know that the function is balanced. And in the circuit composer, we did not get any clear result for some reason. So this is the result. And I have run it on real quantum computer as well. So let's see the result. So yeah, this is the result with 100% probability of being in the state of the qubit first in the state 1 only. So this is what Deutsch-Jozsa algorithm all about. I hope you all understand this clearly. So thank you.